Right now, light from a star 400 light-years away is entering your eyes. That light left its source when Shakespeare was alive, when the pilgrims had not yet sailed, when the world you know did not exist. And here is what most people never realize. You are not looking at a star. You are looking at the past. Every single point of light in the night sky is a time capsule, a message from history, arriving at this exact moment after traveling for years, centuries, sometimes millennia through the void. The farthest galaxies we can see show us the universe as it was 13 billion years ago, before Earth, before the Sun, before anything we would recognize existed. Tonight, we are going to take that idea apart completely. We are going to understand what a light year actually means, not just the definition, but the reality of it, the scale that your brain will resist comprehending, and the deepest mystery at its core. Why light travels at exactly the speed it does, and why that number shapes everything from the atoms in your body to the edge of the observable universe. Before we begin, like and subscribe if this calm, science-driven format resonates with you. Use the hype button if it is available. In the comments, note your location, your current time, and the key question this topic triggers for you. I will address the strongest questions in comments or in a later video. There is something moving through the universe right now that has been traveling since before our planet existed. It left a distant star when dinosaurs had not yet walked the Earth, when the continents wore different shapes, when the oceans held creatures we would not recognize. That something is light. And in approximately 1.3 seconds from now, a beam of it will bounce off the surface of the moon and arrive at your eyes, showing you the lunar surface as it appeared just over a second ago. We rarely think about this. We flip a switch and a room illuminates. We glance at the sun and feel its warmth. We look up at the night sky and see thousands of tiny points scattered across the darkness. But every single one of those experiences involves something so fast, so fundamental, so strange that even after centuries of study, physicists still debate what it truly is. Light moves at 299,792,458 meters per second. That is not an approximation. That is not a rounded figure. That is the exact, defined speed of light in a vacuum, fixed by international agreement in 1983. The meter itself is now defined by this number. 1 meter is the distance light travels in 1,299,792,458 thousandths of a second. Think about that for a moment. We have taken the fastest thing in existence and used it as our ruler. We measure space itself by how far light can go. At this speed, light could circle the Earth approximately 7.5 times in a single second. It could travel from New York to Los Angeles and back again nearly 40 times before you finish blinking. If you could somehow fire a beam of light at a mirror placed on the moon, the reflection would return to you in about 2.5 seconds. These numbers sound impressive when stated quickly, but they fail to capture something essential. Light is not just fast. Light occupies a category entirely its own. Nothing else belongs there. Consider this comparison. The fastest commercial airplane cruises at roughly 900 kilometers per hour. At that speed, circling the Earth once would take about 44 hours. Light does it in 133 milliseconds. A bullet fired from a high-powered rifle travels at perhaps 1,200 meters per second. Light moves 250,000 times faster. Even the electrons flowing through the wires in your home, which travel at a significant fraction of light speed themselves, cannot match a photon racing through empty space. There is fast, there is extremely fast, and then there is light, existing in a realm of velocity that nothing else can touch. In the entire history of physics, across every experiment ever conducted, through every observation ever made, nothing with mass has ever reached the speed of light. Not particles in the largest accelerators humanity has built, not cosmic rays screaming through interstellar space, not the debris flung outward from the most violent supernova explosions. Mass, it seems, is forbidden from traveling that fast, and the reason why reaches into the deepest structure of reality itself. When Albert Einstein published his theory of special relativity in 1905, he was not trying to explain light. He was trying to resolve a contradiction. The equations of electromagnetism, written decades earlier by James Clerk Maxwell, predicted that electromagnetic waves would travel at a specific speed regardless of how the source or the observer moved. This seemed impossible. If you are standing on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone watching from the platform sees the ball moving at 120 kilometers per hour. Speeds add together. That is common sense. That is how the world appears to work. But Maxwell's equation said light does not care about your train. If you shine a flashlight forward while traveling at half the speed of light, the beam does not move at 1.5 times light speed from the perspective of a stationary observer. It still moves at exactly the speed of light. Nothing more, nothing less. The same value, always, regardless of who measures it and how they are moving. Einstein realized this was not a flaw in the equations, it was a feature of the universe. And accepting it meant rethinking everything we believed about space and time. Here is where intuition fails. If light always travels at the same speed for every observer, then something else must give. That something is time itself. As an object moves faster through space, it moves slower through time. This is not philosophy. This is not speculation. This has been measured with atomic clocks flown on airplanes, with particles accelerated to near light speed in laboratories, with satellites orbiting the Earth that must account for time dilation to provide accurate GPS readings. Your smartphone relies on this effect. Without corrections for relativistic time dilation, GPS satellites would drift out of sync, and your location would be off by kilometers within a single day. The universe runs on rules that seem absurd until you realize they are the only rules that work. The closer you approach the speed of light, the more time stretches. At 99% of light speed, time passes approximately 7 times slower for you than for someone standing still. At 99.9%, it slows by a factor of more than 22. Imagine twins, one staying on Earth and one traveling to a nearby star at such speeds. When the traveler returns, they might have aged only a few years, while their sibling has grown old and gray. This is not science fiction. It is the direct mathematical consequence of a universe where light speed is constant for all observers, and at light speed itself, Time stops entirely. This is not a metaphor. For a photon, the fundamental particle of light, there is no passage of time. From the moment a photon is emitted from a distant star to the moment it strikes your eye millions of years later, from your perspective, the photon experiences nothing. No duration, no journey. Emission and absorption are the same instant from its point of view. The photon exists outside of time as we understand it, moving through space in what we would call an eternal present. When you look at starlight, you are seeing something that, from its own frame of reference, has existed for no time at all. This brings us to a question that has troubled physicists for over a century. Why this speed? Why 299,792,458 meters per second and not some other number? Why is there a cosmic speed limit at all? These questions sit at the boundary between physics and philosophy, between what we can measure and what we can only wonder about. The honest answer is that we do not know. The speed of light emerges from Maxwell's equations as a relationship between two fundamental constants, the permittivity and permeability of free space. These describe how electric and magnetic fields behave in a vacuum, how easily space allows electric fields to form, and how readily it permits magnetic fields to propagate. When you combine them mathematically, the speed of light falls out as a natural consequence. It appears in the equations as cleanly as if the universe were designed with this number in mind. But this only pushes the question back one step. Why do those constants have the values they do? Why does empty space have those particular properties? What would happen if they were different? Some physicists argue the question is meaningless. The speed of light is what it is because that is the universe we live in. Asking why is like asking why the number pi equals 3.14159, and so on. It is a feature of mathematical and physical reality that simply exists. Others suspect there may be deeper explanations, perhaps connected to the geometry of space-time itself, perhaps arising from structures in physics we have not yet discovered. String theory and other advanced frameworks attempt to derive such constants from more fundamental principles, but so far, no one has succeeded in explaining why light travels at exactly this speed. What we can say with confidence is that this speed is woven into the fabric of everything. It is not merely the speed at which light travels. It is the speed at which causality propagates. It is the maximum rate at which information can move from one point in the universe to another. It is the conversion factor between mass and energy in Einstein's famous equation. It appears in quantum mechanics, in particle physics, in cosmology, in places that have nothing obvious to do with light at all. The constant C, as physicists call it, is less about light specifically, and more about the fundamental nature of space-time. If the speed of light were different, everything would change. The stars would burn at different rates. Atoms would have different sizes. Chemistry would work differently, if it worked at all. The universe might not permit the existence of complex structures like planets and galaxies and living beings capable of wondering about such things. We exist in a cosmos fine-tuned in countless ways, and the speed of light is one of its most critical parameters. This fine-tuning has led some physicists to wonder whether our universe is one of many, a single bubble in a vast multiverse where different regions have different physical constants. In other universes, light might travel faster or slower. The constants of nature might take different values. Most such universes would be sterile, unable to produce stars or planets or life. We find ourselves in a universe with these particular constants precisely because these constants permit observers to exist. This anthropic argument does not explain why the constants have their values, but it offers a framework for thinking about the question. Whether the multiverse exists remains unknown and perhaps unknowable. What we can say with certainty is that in our universe, light travels at sea, and everything we know about physics depends on this fact. The equations of electromagnetism, the structure of atoms, the behavior of particles, the expansion of the cosmos, all are built upon the foundation of a finite and constant speed of light. Change that foundation, and the entire edifice crumbles. There is a certain humility that comes from contemplating this. We are creatures built from ordinary matter, bound by ordinary physics, living on a small planet orbiting an unremarkable star. We cannot travel at the speed of light. We cannot even come close with our current technology. The fastest human-made object ever, the Parker Solar Probe, reached speeds of about 690,000 kilometers per hour during its close passes by the Sun. That sounds impressive until you realize it is still less than 0.1% of light speed. At that pace, reaching the nearest star would take thousands of years, and yet we can study light. We can measure its speed with extraordinary precision. We can split it into its component wavelengths and read the chemical signatures of stars billions of light years away. We can detect light that left its source before the Earth existed and use it to reconstruct the history of the cosmos. Light is both the barrier we cannot cross and the messenger that tells us everything we know about the universe beyond our small world. When you look up at the night sky tonight, consider what you are really seeing. Not the stars as they are now, but as they were years or centuries or millennia ago. Each photon that enters your eye has been traveling in silence through the void, carrying information from the past, arriving at this precise moment because the universe has rules, and one of those rules is that nothing outruns light. The beam that reaches you is ancient, and yet, from its own perspective, brand new. It has crossed distances your mind cannot truly grasp in a time that, for the light itself, never passed at all. This is the foundation upon which everything else rests. The speed of light defines the scale of the cosmos. It determines how far we can see, how much we can know, how long information takes to travel from one place to another. Before we can understand what a light year means, before we can grasp the distances between stars and galaxies, we must first understand this one fundamental truth. Light is the fastest thing there is, and that fact shapes everything. But how did we discover this? How did human beings, stuck on a small planet with no way to chase a beam of light across the void, figure out exactly how fast it travels? The answer takes us back over 300 years to an astronomer watching the moons of Jupiter, noticing something strange in the timing of their eclipses and realizing that the discrepancy held a secret about the nature of light itself. The deepest mystery of light. We have traveled far in this exploration, from the first measurement of light speed by Ole Rømer watching Jupiter's moons to the cosmic horizons at the edge of the observable universe. We have seen how light defines our units of distance, how it turns telescopes into time machines, how its finite speed isolates stars and galaxies from one another across immense gulfs of space. We have examined time dilation and the strange flexibility of temporal flow for objects approaching relativistic velocities. We have watched Voyager crawl toward its one light-day milestone, a testament to human ingenuity and a reminder of how far we still have to go. And through all of this, one question has lingered beneath the surface, the deepest mystery of all. Why? Why does light travel at exactly 299,792,458 meters per second? Why not faster? Why not slower? Why is there a cosmic speed limit at all? And why is this speed the same for every observer, regardless of their motion, in seeming defiance of all common sense? These questions sit at the boundary between physics and philosophy, between what we can measure and what we can only wonder about. The honest answer is that we do not know. We can describe the speed of light with extraordinary precision. We can derive it from Maxwell's equations as a relationship between the electrical and magnetic properties of empty space. We can show that it must be constant for all observers if the laws of physics are to be the same in every inertial reference frame. But we cannot explain why these properties of space have the values they do, or why the universe is built this way rather than some other way. The speed of light emerges from the permittivity and permeability of free space, two constants that describe how easily electric and magnetic fields propagate through a vacuum. These values are measured, not derived from deeper principles. They are among the fundamental parameters of our universe, alongside the gravitational constant, Planck's constant, and the masses of elementary particles. Some physicists believe that a truly complete theory of physics would derive all these values from a single underlying principle, showing why they must be what they are. Others suspect that these constants may vary in different regions of a much larger multiverse, and that we find ourselves in a universe with these particular values because they happen to permit the existence of complex structures like galaxies, stars, planets, and observers capable of asking why. The constancy of light speed for all observers is perhaps even more mysterious. In Newtonian physics, space and time were absolute. Distances were the same for everyone. Time flowed at the same rate everywhere. Velocities added together in simple arithmetic. This picture worked beautifully for centuries, describing everything from falling apples to orbiting planets. But Maxwell's equations, which describe electromagnetism, did not fit this framework. They predicted a specific speed for electromagnetic waves without reference to any particular observer's motion. The equation seemed to require that light move at the same velocity whether you were standing still or racing toward it at half its speed. Einstein took this apparent contradiction and turned it into a revolution. He proposed that Maxwell's equations were correct and that the Newtonian picture of absolute space and time was wrong. If light's speed is truly constant for all observers, then space and time must be flexible, stretching and compressing to preserve this constancy. Moving clocks run slow. Moving rulers shrink. Simultaneity becomes relative. Two events that appear simultaneous to one observer may happen at different times for another. The entire framework of space and time had to be rebuilt from the ground up. The theory of special relativity has been tested with extraordinary precision. Every prediction it makes has been confirmed. The constancy of light speed is not just an assumption, but an observed fact, verified by the Michelson-Morley experiment, by measurements of particles in accelerators, by the operation of GPS satellites, by countless observations across more than a century. The universe really does work this way. Light really does travel at the same speed for everyone. But why? The mathematical answer is that space-time has a particular geometry, described by the Minkowski metric, in which the speed of light is invariant. But this just pushes the question back a level. Why does space-time have this geometry? Why are space and time unified in this particular way? Why is there a maximum speed at all? Some physicists point to causality. If information could travel faster than light, effects could precede their causes in some reference frames. You could receive a message before it was sent. You could observe the result of an event before the event occurred. This would create logical paradoxes and undermine the very notion of cause and effect. The speed of light may be the universe's way of preserving the logical structure of events, ensuring that causes always precede effects for every observer. Others suggest that the speed of light is not special to light at all, but is simply the speed of causality, the maximum rate at which any influence can propagate through space-time. Light travels at this speed because photons are massless, and massless particles must move at the universal speed limit. Gravity waves also travel at this speed. So would any other massless phenomenon. The constant c is less about light specifically and more about the deep structure of space-time itself. This perspective reframes our understanding. We do not ask why light is so fast. We ask why causality has a speed limit, and why that limit has the particular value it does. The question shifts from the properties of light to the properties of space-time, from electromagnetism to the geometry of the universe. Light is simply one phenomenon among several that travels at this fundamental speed. It is the most familiar because we evolved to detect it, but it is not unique. Gravitational waves, detected for the first time in 2015, travel at the same speed. When two black holes merge billions of light years away, the ripples in space-time they create propagate at exactly c, carrying information about the collision across the cosmos. These waves arrived at Earth at the same moment as any light from the event would have, confirming that c is not just the speed of light, but the speed of gravity as well. Einstein predicted this over a century ago. Modern detectors have confirmed it with exquisite precision. Space-time has a speed, and that speed is c. There are also those who wonder whether the speed of light might have been different in the early universe, or might vary in different regions of the cosmos. Some theoretical models propose that CE could have been higher shortly after the Big Bang, potentially helping to explain why distant regions of the universe appear so similar, despite having no causal contact under standard physics. These ideas remain speculative, lacking observational confirmation, but they illustrate how the constancy of light speed is not taken for granted even by physicists. It is questioned, probed, tested, and wondered about. The fine structure, constant, a dimensionless number that characterizes the strength of electromagnetic interactions, depends on the speed of light, along with other fundamental constants. If this number were significantly different, atoms would behave differently, chemistry would change, and life as we know it might be impossible. The speed of light is not just a curiosity of physics. It is intimately connected to the conditions that allow complexity and consciousness to exist. In a universe with a very different value of c, there might be no one to ask why. This brings us to the deepest level of mystery. We can measure the speed of light. We can describe its consequences. We can use it to explore the cosmos and build technologies that depend on its constancy. But we cannot step outside the universe and ask why it was made this way. We are embedded in the very fabric we are trying to understand. The speed of light is part of our reality, as fundamental as the existence of space and time themselves. Asking why it has its particular value may be like asking why there is something rather than nothing. The question is valid, but the answer, if one exists, lies beyond the reach of current science. Perhaps future theories will illuminate this darkness. Perhaps string theory, or loop quantum gravity, or some framework yet to be invented will derive the speed of light from more fundamental principles. Perhaps we will discover that c is not arbitrary, but necessary, the only value compatible with a consistent universe. Or perhaps we will find that it is one of many possibilities, realized in our particular corner of a vast multiverse, with other values prevailing elsewhere. For now, the speed of light remains both our greatest tool and our greatest mystery. It tells us how to measure the cosmos. It tells us how far we can see, how long signals take to travel, how time and space bend for objects in motion. It shapes everything from the structure of atoms to the horizons of the observable universe. And it whispers, beneath all its uses, a question we cannot yet answer. Why this number and no other? We began this journey with a simple concept. A light year is the distance light travels in 1 year. We end it having glimpsed how much that simple concept contains. The speed of light is not just a number. It is the heartbeat of the cosmos, the rhythm that synchronizes space and time, the constant against which all motion is measured. To understand a light year is to understand that we live in a universe built on rules we can discover but not fully explain, a universe that reveals its workings to patient observers while keeping its deepest secrets hidden. The stars will still be there tomorrow night, scattered across the sky like ancient beacons. The light entering your eyes will still have traveled years or centuries to reach you. The distances will still be incomprehensible by any human standard, but perhaps now you will see them differently. Not as fixed points, but as messages from the past. Not as nearby, but as impossibly far, separated by gulfs that even light takes years to cross. Not as eternal, but as snapshots of moments long gone, frozen in photons that have finally arrived. This is the gift of understanding light years. Not mastery over distance, for we remain bound to our small planet. But perspective, a sense of where we are in the vastness of space and time, an appreciation for the patience of light, traveling endlessly through the void, carrying news from star to star, from galaxy to galaxy, from the beginning of time to the present moment. Each photon that reaches us has been traveling since before we were born, since before our species existed, since before our planet formed. They are ancient messengers, faithful and tireless, bringing word of events long past to eyes newly opened. Thank you for taking this journey. Thank you for staying through the numbers and the scales and the strangeness. If this calm, science-driven exploration has given you something to think about, consider leaving a like or sharing it with someone who might also appreciate a quiet hour contemplating the cosmos. A brief note as we close. Nothing presented here should be taken as medical, financial, or professional advice. This is a work of scientific curiosity and entertainment, an invitation to wonder rather than a prescription for action. The universe is vast and strange and full of mysteries. We explore them together, humbly, knowing that our knowledge is always incomplete. And now, as the light from distant stars continues its ancient journey, as Voyager drifts ever farther from home, as the observable universe slowly expands and the cosmic horizons recede, perhaps it is time to rest. The questions will still be here tomorrow. The stars will still be shining. The light will still be traveling, patient and constant, measuring the distances that define our universe. Good night, sleep well, and may your dreams take you to the stars, where light has already traveled, where time flows differently, where the universe waits with patience older than worlds. The first person to catch light. In 1676, a young Danish astronomer sat in the Paris Observatory, watching Jupiter through a telescope and recording the precise moments when its innermost large moon vanished into the planet's shadow. His name was Ole Rømer, and he was about to make one of the most important discoveries in the history of science, almost by accident. He was not trying to measure the speed of light. He was trying to solve a problem with clocks. The 17th century was an age of exploration and empire, and the great naval powers of Europe faced a persistent challenge. Ships at sea needed to know their longitude, their east-to-west position on the globe, but determining longitude required knowing the exact time back home while simultaneously knowing the local time at sea. Local time was easy. You could observe when the sun reached its highest point. But knowing what time it was in Paris or London while you drifted somewhere in the Atlantic was nearly impossible. Clocks of that era could not keep accurate time on a rolling ship. The pendulum swung erratically with the waves. Springs lost their tension. A clock that kept perfect time on land would drift by minutes or hours over a long voyage, and those errors translated into navigational disasters. Ships running aground on coasts they thought were hundreds of miles away. Galileo had proposed a solution decades earlier. Jupiter has 4 large moons, visible through even a modest telescope, and these moons orbit the planet with clockwork regularity. The innermost moon, Io, completes an orbit in approximately 42.5 hours, disappearing behind Jupiter and reappearing on the other side like a cosmic metronome. If astronomers could create precise tables predicting exactly when Io would enter Jupiter's shadow, Sailors anywhere on Earth could observe the eclipse, compare it to the predicted time, and calculate their longitude from the difference. Jupiter's moons would become a universal clock, visible from any ocean. The problem was that the predictions did not quite work. Astronomers had been tracking Io's eclipses for years, and they noticed something strange. Sometimes Io emerged from Jupiter's shadow a few minutes earlier than predicted. Sometimes it emerged a few minutes later. The discrepancies followed a pattern tied to Earth's position in its orbit around the Sun. When Earth was moving toward Jupiter, the eclipses came slightly early. When Earth was moving away from Jupiter, they came slightly late. The total variation amounted to about 22 minutes over the course of a year. Most astronomers assumed this was some unknown property of Io's orbit, perhaps a wobble or irregularity they had not yet accounted for. But Rømer saw something different. He realized that the timing variations corresponded precisely to changes in the distance between Earth and Jupiter. When Earth was on the same side of the Sun as Jupiter, the two planets were relatively close. When Earth was on the opposite side, they were much farther apart. The difference in distance across Earth's orbit was enormous, roughly the diameter of our path around the Sun, about 300 million kilometers. Rømer proposed a radical explanation. Light, he suggested, was not instantaneous. It took time to travel from Jupiter to Earth. When Earth was closer to Jupiter, the light from Io's eclipse had less distance to cover and arrived sooner. When Earth was farther away, the light had to travel that extra distance and arrived later. The 22-minute variation was not a quirk of Io's orbit. It was the time required for light to cross the diameter of Earth's orbit. This was a stunning claim. For centuries, philosophers and scientists had debated whether light traveled instantaneously or at some finite speed. The ancient Greeks argued about it. Galileo himself had tried to measure light's speed by stationing assistants on distant hilltops with lanterns, uncovering their lights in sequence and trying to detect a delay. He found none, which told him only that light was either instantaneous or far too fast for human reflexes to measure. Now Rømer was claiming he had measured it, using Jupiter as his laboratory and the solar system as his ruler. In September of 1676, Rømer made a prediction. He announced to the French Academy of Sciences that an upcoming eclipse of Io on November 9th would occur 10 minutes later than the standard tables predicted. His colleagues were skeptical. How could anyone know such a thing in advance? But when November 9th arrived and astronomers turned their telescopes toward Jupiter, Io emerged from the planet's shadow exactly 10 minutes late, precisely as Rømer had forecast. The scientific world took notice. Here was not merely a hypothesis, but a successful prediction, the gold standard of scientific proof. Rømer had demonstrated that light traveled at a finite speed and had provided a method to calculate it. Using the best estimates available for the diameter of Earth's orbit, which were not particularly accurate in his time, Rømer computed a speed of roughly 220,000 kilometers per second. This was about 26% lower than the modern value, but the error lay in the imprecise knowledge of astronomical distances, not in Rømer's method. His logic was sound. His observation was correct. For the first time in human history, someone had caught light in the act of traveling and measured how fast it moved. Not everyone was convinced immediately. The great astronomer Giovanni Cassini, who directed the Paris observatory where Rømer worked, remained skeptical. The Dutch scientist Christian Huygens, however, embraced Rømer's findings and used them in his own work on optics. Isaac Newton, who was developing his theories of light and gravity in England, accepted the finite speed of light as established fact. Over the following decades, as measurement techniques improved and the dimensions of the solar system became better known, Rømer's basic result was confirmed again and again. The method Rømer used seems almost impossibly clever in retrospect. He could not chase a beam of light. He could not set up mirrors at the vast distances required, but he recognized that the solar system itself was his instrument. Earth's motion around the Sun created a natural experiment, varying the distance to Jupiter by hundreds of millions of kilometers over the course of a year. Eo's regular eclipses provided precise timing signals. The combination revealed what no laboratory of the era could have measured directly. 50 years after Rømer's discovery, an English astronomer named James Bradley found independent confirmation through an entirely different method. Bradley was trying to measure the parallax of stars, their apparent shift in position as Earth orbited the Sun, which would allow calculation of stellar distances. Instead, he noticed a different kind of shift, a small but consistent displacement in the apparent positions of all stars related to the direction of Earth's motion. This stellar aberration, as it came to be called, was caused by the combination of Earth's velocity and the finite speed of starlight. Just as rain falling vertically appears to slant toward you when you run through it, starlight appeared to shift slightly in the direction of Earth's orbital motion. From the magnitude of this shift, Bradley calculated a speed of light that agreed well with Rømer's estimate and was even more accurate. By the 19th century, physicists had developed methods to measure the speed of light entirely on Earth's surface. In 1849, the French physicist Hippolyte Fizeau used a rapidly spinning toothed wheel and a mirror placed several kilometers away. Light passed through a gap in the wheel, traveled to the mirror, reflected back, and either passed through the next gap or was blocked by a tooth, depending on how fast the wheel spun. By adjusting the rotation speed until the returning light was completely blocked, Fizeau could calculate how long the light had taken to make its round trip. His result was within 5% of the modern value. The elegance of Fizeau's method lay in its simplicity. He did not need astronomical distances or planetary alignments. He needed only a bright light source, a toothed wheel, a mirror, and careful measurement of rotation speed. The apparatus fit in a single laboratory, yet it captured one of the most fundamental constants in nature. Physics had brought the cosmos down to Earth. Léon Foucault improved on Fizeau's method by using a rotating mirror instead of a toothed wheel. The rotating mirror directed light toward a distant fixed mirror, and by the time the light returned, the rotating mirror had moved slightly. The angle of deflection revealed the time elapsed, and thus the speed of light. Foucault's refinement allowed even more precise measurements and could be conducted over shorter distances, making the experiment more practical. Albert Michelson, working in the late 19th and early 20th centuries, refined these techniques to extraordinary precision, eventually measuring the speed of light to within a fraction of a percent of today's defined value. Michelson's work on light earned him the Nobel Prize in 1907, the first American to receive the award in physics. Each generation of physicists found new ways to measure this fundamental constant with greater and greater accuracy. Radio waves, microwaves, lasers, interferometers, atomic clocks, all were pressed into service. By the late 20th century, measurements had become so precise that the uncertainty lay not in our knowledge of light's speed, but in our definition of the meter itself. In 1983, the scientific community made a remarkable decision. They fixed the speed of light at exactly 299,792,458 meters per second by definition, and redefined the meter in terms of light. The chase was over. We had measured light so thoroughly that we now used it to define our units of measurement. But let us return for a moment to Ole Rømer, watching Jupiter from the Paris Observatory nearly 350 years ago. He could not have imagined where his discovery would lead. He did not know about relativity, about photons, about the electromagnetic spectrum. He was simply trying to make better predictions about a moon's eclipses. And yet, he grasped something essential, something that would reshape physics, that would eventually lead to Einstein, to nuclear energy, to our understanding of the cosmos itself. Light is not magic. Light is not instantaneous. Light is a physical phenomenon that obeys physical laws, and those laws can be discovered by careful observation and clever reasoning. There is a certain poetry in the fact that our first measurement of light's speed came from watching the heavens. We did not catch light in a laboratory. We caught it crossing the solar system, and in doing so, we began to understand the scale of the universe we inhabit. Rømer showed that even the vast distance from Earth to Jupiter was not instantaneous for light to cross. That distance is merely a prelude. The stars are immensely farther. The galaxies are farther still. And to describe those distances, we would need a new kind of unit, one built not from meters or kilometers, but from light itself and the time it takes to travel. This is where the light year enters the story. It is not a measure of time despite its name. It is a measure of distance, the distance light travels in one Earth year. And that distance, as we are about to discover, is so vast that it forces us to reimagine everything we think we know about far and near, about here and there, about the scale of existence itself. Distance, written in time. 9,460,730,472,580.8 kilometers. That is 1 light year. Say it aloud, and the number becomes meaningless, a string of syllables that the human mind cannot convert into anything resembling an image. We have no reference point for such a figure. The largest distances most of us ever travel might be a few thousand kilometers on a vacation flight. The circumference of the entire Earth is only about 40,000 kilometers. Even the distance from Earth to the Moon, which took Apollo astronauts 3 days to cross, is merely 384,000 kilometers. A light year exceeds these familiar distances not by factors of 10 or 100, but by factors of millions and billions. Let us try to build up to it slowly. Light travels at roughly 300,000 kilometers per second. In 1 second, Light could span the distance from New York to Los Angeles more than 40 times. In the time it takes you to draw a single breath, light has crossed a distance greater than most humans will travel in their entire lives. 1 second of light travel equals approximately 300,000 kilometers. That is a light second. Now extend this. In 1 minute, light covers roughly 18 million kilometers. In 1 hour, it travels about 1,080,000,000 kilometers. This is the distance light crosses while you watch a movie or sleep through the night. 1 billion kilometers, a number already beyond ordinary comprehension. Jupiter orbits the Sun at an average distance of about 780 million kilometers. Light from the Sun reaches Jupiter in approximately 43 minutes. Saturn, farther out, receives its sunlight after about 79 minutes. These gas giants, so remote that spacecraft take years to reach them, sit within an hour or two of the Sun by the measure of light. Keep extending. 1 day of light travel covers roughly 26 billion kilometers. This is more than the distance from the Sun to Neptune, the most distant major planet in our solar system. 1 week of light travel extends to about 180 billion kilometers. 1 month reaches nearly 800 billion kilometers. And 1 year, the full rotation of our planet around the Sun, the cycle of seasons, the passage from one birthday to the next. In that time, light travels 9.46 trillion kilometers. Trillion? We use this word casually now in discussions of government budgets and national debts, but we rarely pause to consider what it means. A trillion is a million millions. If you counted one number per second, reaching a trillion would take over 31,000 years. If you stacked 1 trillion sheets of paper, the pile would reach past the moon. And light crosses 9.5 trillion kilometers every single year, without stopping, without slowing, a distance so incomprehensible that astronomers invented a new word just to contain it. The light year is a peculiar unit. It sounds like a measure of time because it contains the word year, and this confusion persists even among people who should know better. Science fiction sometimes uses it incorrectly. Characters saying things like, "It will take us 3 light years to reach the station," when they mean it will take 3 years traveling at light speed. But the light year is purely a unit of distance. It tells us nothing about how long a journey will take unless we happen to be traveling at the speed of light, which, as we have established, is impossible for anything with mass. The confusion is understandable. We have no everyday experience with distances so vast that they require time-based units. We measure the walk to the grocery store in blocks or meters. We measure the drive to another city in kilometers or miles. We measure flights across continents in hours, implicitly converting distance to time based on aircraft speed. But the light year does something different. It uses the ultimate speed, the cosmic maximum, to define a distance so immense that no other unit would be practical. Imagine trying to express stellar distances in kilometers. The nearest star is about 40 trillion kilometers away. The center of our galaxy is about 250 quadrillion kilometers distant. The Andromeda Galaxy lies roughly 24 quintillion kilometers from Earth. These numbers are not just large, they are actively hostile to comprehension. The zeros pile up until the figures become meaningless strings of digits. The light year rescues us from this absurdity by packaging vast distances into manageable numbers. 4.24 light years to Proxima Centauri, 26,000 light years to the galactic center, 2.5 million light years to Andromeda. The numbers remain large, but they are comprehensible. They fit in human memory. They can be compared and discussed. Why measure distance in time at all? The answer lies in convenience and comprehension. Astronomical distances are so vast that conventional units become absurd. The nearest star system to our Sun, Alpha Centauri, lies about 40 trillion kilometers away. Writing that number repeatedly in scientific papers and textbooks would be cumbersome and error-prone. But saying Alpha Centauri is 4.24 light-years away communicates the same information in a form that astronomers can work with. It also carries an intuitive meaning. If you could travel at light speed, the journey would take 4.24 years. The unit of distance implies a unit of time, linking the two in a way that proves useful for thinking about cosmic scales. There is another unit astronomers frequently use, the parsec, which equals approximately 3.26 light years. Parsecs arise from the geometry of parallax measurements, a method for determining stellar distances that involves observing how stars appear to shift position as Earth orbits the Sun. Professional astronomers often prefer parsecs for technical work, but light years remain popular for public communication because they are easier to understand. Most people can imagine a year passing. Few people can visualize the trigonometric abstraction of a parsec. Here is an analogy that might help ground the light year in something relatable. Robert Burnham, the astronomer who compiled the famous Celestial Handbook, noticed a curious coincidence. There are approximately 63,000 astronomical units in a light year. An astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. By pure chance, there are also approximately 63,000 inches in a mile. This means that if we shrink the astronomical unit down to 1 inch, a light year becomes 1 mile. Think about that scale. The Sun is a grapefruit sitting on a table. Earth is a pinhead 1 inch away. The Moon is a speck of dust a 1/4 inch from the pinhead. Mars, at its closest, is about 1/2 inch farther out. Jupiter is 5 inches from the grapefruit. Saturn is 10 inches. Neptune, the most distant planet, is 30 inches away, less than a yard. The entire solar system, all the planets and their moons, all the asteroids and comets, fits within a circle roughly 1 yard in radius if we use the orbits of major planets, or perhaps a bit larger if we include the distant Kuiper belt. Now consider the nearest star. Proxima Centauri, the closest star to our Sun, lies at a distance of about 4.24 light years. In our scaled model, that is 4.24 miles away. The grapefruit Sun sits on your table. The nearest other grapefruit is 4 miles down the road, and this is the closest one. Most stars in our galactic neighborhood are tens or hundreds of miles away at this scale. The center of the Milky Way galaxy, roughly 26,000 light-years distant, would be 26,000 miles away, more than the circumference of Earth. And the Andromeda galaxy, our nearest large galactic neighbor, at 2.5 million light-years would be 2.5 million miles distant, about 10 times the real distance from Earth to the Moon. The scale model breaks down precisely because the distances become absurd, even when shrunk by factors of billions. Space is mostly empty. The stars are lonely points scattered across a void so vast that even light, the fastest thing there is, takes years to cross from one to the next. When we look at the night sky and see what appears to be a crowded field of stars, we are being deceived by perspective. Those stars are incomprehensibly far apart. If you could shrink yourself down and fly through our galaxy like a cosmic insect, you would notice mostly nothing at all. Darkness and vacuum stretching in every direction, with tiny points of light appearing at enormous intervals. This emptiness has profound implications. It means that even within our own galaxy, the space between stars is almost perfectly empty. A cubic light year of interstellar space contains, on average, only about 1 atom of hydrogen. Compare this to the air you breathe, which contains roughly 25 quintillion molecules per cubic centimeter. Space is empty in a way that nothing on Earth can prepare you for. The stars are oases of matter and energy, separated by deserts of absolute nothingness. The emptiness also explains why interstellar travel is so difficult. There is nothing to push against, nothing to grab onto, nothing to refuel from. A spacecraft traveling between stars must carry everything it needs for the entire journey. All its propellant, all its energy, all its supplies. There are no gas stations in the void, no rest stops, no rescue missions if something goes wrong. The light years between stars are measured not just in distance but in isolation, in the absolute separation from any help or resources. This emptiness is itself significant. It means that the universe is not a cozy place where civilizations might easily visit one another. It means that even if intelligent life exists on a planet orbiting Proxima Centauri, sending a message and receiving a reply would take nearly 9 years. A conversation spanning those 4 light years would be like exchanging letters with someone in the 18th century, each response arriving years after the question was asked. The light year measures not only distance but isolation. It tells us how alone each island of light is in the cosmic ocean. And yet the light year also carries a kind of hope. Because light takes time to travel, the universe has given us a gift. When we look at Proxima Centauri, we see it as it was 4 years ago. When we look at the star Vega, 25 light years away, we see it as it existed when you were perhaps a child, or when your parents were young. When we look at the Andromeda galaxy, we see it as it was 2.5 million years ago, when our ancestors were just beginning to walk upright on the African savanna. The light year makes the universe into a time machine. The farther we look, the deeper into history we see. This will become crucial as we continue our journey. For now, hold this number in your mind: 9.46 trillion kilometers, the distance light travels while Earth completes one orbit around the Sun. A measurement so large, it took humanity thousands of years just to realize such distances existed, and longer still to find ways to measure them. The stars that decorate our night sky are not just far away, they are light years away. And understanding what that truly means requires us to think about light not as something that illuminates our world instantaneously, but as a traveler crossing an ocean of space, carrying messages from the past into the present. The Sun, our own star, sits roughly 8 light minutes away. Its warmth on your face left the solar surface 500 seconds ago, but 8 light minutes is almost nothing on the cosmic scale. To reach even the nearest other star takes light more than 4 years. To cross our galaxy requires 100,000 years. To span the distance to neighboring galaxies takes millions of years. And the observable universe, everything we can possibly see, stretches 46 billion light years in every direction. A sphere of ancient light arriving from an inconceivable past. The light year gives us a vocabulary for these immensities. Without it, we would drown in zeros, lost in numbers too large to speak or write. With it, we can begin to map the cosmos, to chart the islands of light scattered through the darkness, to understand just how far there is between here and anywhere else. 8 minutes from the Sun. Right now, at this very moment, you are not seeing the Sun as it is. You are seeing the Sun as it was approximately 8 minutes and 20 seconds ago. If our star were to suddenly vanish, blinking out of existence without warning, you would continue to feel its warmth and see its light for another 8 minutes before the darkness reached you. This is not a philosophical abstraction. This is the physical reality of living 8 light minutes from your star. We speak casually about the Sun being 93 million miles away, or 150 million kilometers, but these numbers have lost their meaning through repetition. We hear them in school, read them in textbooks, and they slide past our attention like so many facts to be memorized and forgotten. But translate that distance into light travel time and something shifts. 8 minutes, the length of a shower, the duration of a song, the time it takes to hard-boil an egg. In that brief window, light crosses the entire gulf between the Sun and Earth, a journey that would take a car driving at highway speed more than 170 years to complete. This is the scale of our cosmic neighborhood, not the vast gulfs between stars, not the mind-bending distances to other galaxies, just our own solar system, the collection of planets and moons and debris that orbits our particular star. And even here, in our own backyard, light travel time introduces delays that have shaped both our understanding of the universe and our ability to explore it. Consider the moon. It hangs in our sky, seemingly close enough to touch on a clear night. The Apollo astronauts crossed the distance in 3 days, and yet light makes the journey in 1.3 seconds. When Neil Armstrong reported his first step onto the lunar surface, mission controllers in Houston heard his words 1.3 seconds after he spoke them. The delay was barely noticeable, a slight hesitation in conversation. But it was there, a tiny reminder that even our nearest celestial neighbor is not instantaneously connected to us. Move outward through the solar system, and the delays grow. Mars, when it swings closest to Earth, is about 3 light minutes away. During a more distant opposition, when our planets are on opposite sides of the Sun, Mars can be over 20 light minutes away. This creates a fundamental challenge for operating spacecraft on or near Mars. When the Curiosity rover encounters an obstacle, mission controllers cannot simply grab a joystick and steer it around. They send a command, wait at least 6 minutes for the signal to reach Mars, then wait another 6 minutes or more to learn whether the command succeeded. The rover must be designed with enough autonomy to make certain decisions on its own, to recognize hazards and stop before controllers even know there is a problem. The Mars rovers, Spirit and Opportunity, Curiosity, and Perseverance have all operated under this light speed constraint. Engineers developed sophisticated software to give these machines a degree of independent judgment, the ability to analyze terrain, plan routes, and execute maneuvers without constant human oversight. This is not science fiction artificial intelligence. It is practical necessity forced upon us by the speed of light. We cannot have real-time conversations with our machines on Mars. We send instructions into the void and wait, hoping we anticipated every contingency. Jupiter, the giant of our solar system, orbits at an average distance of about 43 light minutes from the Sun, which means it can be anywhere from roughly 33 to 52 light minutes from Earth, depending on orbital positions. When the Galileo probe plunged into Jupiter's atmosphere in 1995, transmitting data about conditions no spacecraft had ever directly measured, that data took the better part of an hour to reach Earth. Scientists listening to the transmission knew that whatever was happening to the probe had already happened. The spacecraft had already been crushed by Jupiter's immense atmospheric pressure by the time its final signals arrived. Saturn is farther still, roughly 70 to 90 light minutes away. Uranus ranges from about 2.4 to 2.8 light hours distant. Neptune, the outermost major planet, is over 4 light hours away. And Pluto, when it swings to its farthest point from the Sun, can exceed 5.5 light hours. The New Horizons spacecraft, which flew past Pluto in 2015, operated at such distance that a single command and response cycle took over 9 hours. The flyby itself was executed entirely by onboard programming. There was no possibility of real-time control. The spacecraft approached Pluto at 14 kilometers per second, gathered its data in a matter of hours, and only afterward began the long process of transmitting its findings back to Earth. A download that took over a year due to the extreme distance and the limited power of its transmitter. Beyond Neptune lies the Kuiper Belt, a region of icy bodies that extends to perhaps 50 astronomical units from the Sun, or about 7 light hours. Beyond that is the scattered disk and the hypothetical Oort cloud, a vast sphere of comets that may extend a quarter of the way to the nearest star, tens of thousands of astronomical units outward, a region so distant that light takes weeks or months to cross it. Our solar system is not a compact, tidy arrangement of planets. It is a sprawling domain, stretching light hours in every direction, with the Sun as a tiny bright point at the center, and everything else scattered through the darkness like dust motes in a cathedral. The Voyager spacecraft, launched in 1977, have now traveled farther from Earth than any human-made object. Voyager 1, as of today, is over 23 billion kilometers from Earth, which translates to roughly 22 light hours. When mission controllers send a command to Voyager 1, the signal travels at light speed for nearly a full day before reaching the spacecraft. The response takes another day to return. A simple ping, a confirmation that the spacecraft is still functioning, requires almost 44 hours of waiting. This delay has shaped how the Voyager mission operates. There is no real-time piloting, No joystick control, no ability to respond instantly to unexpected situations. Everything must be planned in advance. Commands are uploaded in batches. The spacecraft executes them autonomously. Data is transmitted back in scheduled bursts. The mission team watches events unfold a full day after they occur. Passive observers of a machine that must fend for itself. The psychological effect on mission controllers is significant. When something goes wrong, and things have gone wrong, the team knows about it hours after it happened. The spacecraft has already dealt with the problem or failed to deal with it before anyone on Earth receives word. The emotions of mission control are always out of phase with reality. Celebrations happen a day late. Worries emerge for events already resolved. The flow of time between Earth and Voyager has been stretched to the point where immediacy becomes meaningless, and Voyager is approaching a milestone. In late 2026, it will reach a distance where light from the Sun takes a full 24 hours to arrive. One light day from the star that gave it birth. This seems like a vast distance, and in human terms, it is. But consider this. Voyager 1, traveling at 17 kilometers per second, has been flying away from Earth for nearly 50 years. At its current speed, it would need another 73,000 years to reach Proxima Centauri, the nearest star. One light day is nothing compared to 4.24 light years. Voyager has barely left the driveway. This is the humbling truth that light travel time reveals. Our fastest spacecraft, the culmination of decades of aerospace engineering, are pathetically slow on cosmic scales. The Parker Solar Probe, which holds the record for fastest human-made object, reached speeds of 690,000 kilometers per hour during close passes by the Sun. That is fast enough to fly from New York to Tokyo in less than a minute. It is also less than 0.07% of light speed. At that velocity, reaching Proxima Centauri would take over 6,000 years. The distances within our solar system, measured in light minutes and light hours, are manageable for robotic exploration, but agonizing for communication. We have never had a real-time conversation with any spacecraft beyond the Moon. We send messages into the void and wait. The distances to nearby stars, measured in light years, are effectively insurmountable for any technology we currently possess or can reasonably imagine building. A generation ship traveling at 1% of light speed would take over 400 years to reach Alpha Centauri. At a more achievable fraction of a percent of light speed, the journey would take millennia. And yet we keep reaching. We send our robotic emissaries to the outer planets, accepting the hours of delay, engineering our spacecraft to be patient and autonomous. We dream of missions to the nearest stars, conceptualizing solar sails and nuclear pulse drives and technologies that might someday close the gap between light minutes and light years. The distance is not a wall, it is a challenge, and humanity has always found ways to extend its reach, to shrink the world with roads and ships and aircraft and rockets, to make distant places feel closer than they were before. But for now, the Sun remains 8 light minutes away. Mars remains at least 3. Jupiter and Saturn hover around the hour mark, while the outer reaches of our solar system stretch into light hours and beyond. These are not abstractions. These are the delays our spacecraft experience, the lags in our cosmic conversations, the proof that even within our own planetary system, distance imposes limits on knowledge and communication. The next time you feel the sun on your face, remember that warmth began its journey before you stepped outside. The light entering your eyes carries information from 8 minutes in the past. If the sun went dark, you would not know for 500 seconds. You live, as we all do, in a delayed broadcast of the universe, receiving signals that left their sources some time ago, never quite knowing the present state of anything beyond your immediate surroundings. This is not a limitation we can engineer away. It is the nature of space-time itself, and it applies everywhere at every scale, from the light minutes of the solar system to the light years of the stars, the telescope as time machine. There is a form of time travel available to anyone willing to step outside on a clear night and look up. No machine required, no exotic physics, no paradoxes to resolve. Simply raise your eyes to the stars and you are looking backward through time, seeing the universe not as it is but as it was, receiving light that began its journey before you were born, before your grandparents were born, in some cases before the human species existed at all. This is not metaphor. This is the straightforward consequence of light traveling at a finite speed across vast distances. When you look at the moon, you see it as it appeared 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. And when you look at the stars scattered across the night sky, you see them as they were years, decades, centuries, or millennia in the past. The farther the star, the deeper into history you gaze. Consider Sirius, the brightest star in the night sky, a blazing point of light in the constellation Canis Major. Sirius is 8.6 light-years away. The photons striking your retina tonight left that star 8.6 years ago. Whatever Sirius is doing at this exact moment, you will not know for another 8.6 years. The star you see is a time capsule from the recent past, bright and blue-white, one of the closest stellar neighbors to our Sun. Move your gaze to Vega, the brilliant star nearly overhead on summer evenings in the northern hemisphere. Vega lies 25 light-years away. Its light has been traveling since a quarter century ago. A child born, the moment that light left Vega, would now be an adult, perhaps with children of their own. The star appears fixed and unchanging in the sky, but it is a window to events that occurred during a different chapter of human history. Polaris, the North Star, sits roughly 430 light-years distant. When the light you see tonight departed Polaris, Galileo had not yet turned his telescope toward the sky. Shakespeare had not written his greatest plays. The Pilgrims had not sailed to the New World. You are seeing a star from the era of the Renaissance, a beam of light that has outlasted empires. And these are merely the nearby stars, the ones bright enough to see with the naked eye. Pull out a telescope or binoculars, and you can see objects vastly more distant. The Orion Nebula, that hazy patch of light in Orion's sword, is approximately 1,300 light-years away. The light reaching your eyes tonight left that stellar nursery when Europe was in the early medieval period, when the Roman Empire had fallen, but the Crusades had not yet begun. Stars are being born in that nebula right now, but we will not see their first light for over a millennium. The Pleiades, the beautiful star cluster that rises in autumn, lies about 440 light-years away. The Beehive cluster in Cancer is closer, roughly 577 light-years. Messier 13, the Great Globular Cluster in Hercules, sits 22,000 light-years from Earth. When you observe it through a telescope, you are seeing a swarm of ancient stars as they appeared when mammoths still walked the Earth, when the last ice age was in full grip, when our ancestors were painting on cave walls and hunting with stone tools. Push farther. The Andromeda Galaxy, visible to the naked eye as a faint smudge on dark nights, is 2.5 million light-years away. The light from Andromeda that enters your eye tonight began its journey when the genus Homo was just emerging in Africa, when our ancestors were not yet recognizably human. Andromeda has been hurtling toward the Milky Way this entire time, closing the gap at roughly 110 kilometers per second. But the collision will not occur for another 4 billion years. You are watching a galaxy frozen in the deep past, an image from the early Pleistocene preserved in photons. And even Andromeda is close by cosmic standards. The Hubble Space Telescope and the James Webb Space Telescope have captured images of galaxies billions of light-years away. When we look at these objects, we see them as they were billions of years in the past, when the universe was young, when galaxies were still forming, when the first stars were igniting in the primordial darkness. The light from the most distant objects ever observed began its journey less than 1 billion years after the Big Bang. We are not merely looking far away. We are looking back to the cosmic dawn. This has profound implications for astronomy. When scientists study distant galaxies, they are not learning about the current state of those galaxies. They are studying the universe's past, reconstructing its history by examining objects at different distances, each one a snapshot from a different era. A galaxy 1 billion light-years away shows us the universe 1 billion years ago. A galaxy 10 billion light-years away shows us conditions when the cosmos was less than a third of its current age. By surveying objects at varying distances, astronomers can piece together how galaxies form, evolve, merge, and die, watching the entire cosmic story unfold across time. The cosmic microwave background radiation, the afterglow of the Big Bang, represents the farthest back we can see using light. This radiation was released approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely through space. That light has been traveling ever since, redshifted by the expansion of the universe from visible light into microwaves. When we detect the cosmic microwave background, we are seeing the universe as a baby, a mere few 100,000 years old before stars or galaxies existed. The radiation comes from a shell of space about 46 billion light-years away in today's terms, accounting for cosmic expansion, but it shows us conditions from 13.8 billion years ago. There is something both humbling and exhilarating about this. Every photon that reaches us is a messenger from the past. The universe has no instant updates, no real time feed. We exist in a kind of cosmic isolation, each point in space receiving delayed news from everywhere else. The sun could explode, and we would have 8 minutes of continued ignorance. A nearby star could be engulfed by an expanding supernova right now, and we might not see the flash for years or decades. The present is a local phenomenon. Beyond our immediate surroundings, we know only the past. And yet this limitation is also a gift. Because light has a finite speed, we can study the history of the universe simply by looking at different distances. We do not need to travel through time. We do not need to excavate cosmic fossils. We simply build larger telescopes and point them at fainter, more distant objects. Each improvement in our observational capability pushes our view deeper into the past. The James Webb Space Telescope was designed specifically to see farther back than ever before, to capture light from the first galaxies that formed after the cosmic dark ages. Its images are archaeology on a cosmic scale, revealing structures that existed when the universe was only a few % of its current age. Consider what this means for the search for life elsewhere. If intelligent beings exist on a planet orbiting Proxima Centauri, and if they are looking at Earth through their own telescopes, they see our planet as it was 4 years ago. They see our lights, our atmosphere, our continents, all delayed by the light travel time. If a civilization exists in the Andromeda galaxy, their telescopes might show them Earth, but an Earth from 2.5 million years ago, a planet with no human presence at all. They would see the landscape of early hominids, an Earth untouched by civilization. Our entire recorded history, all our cities and wars and achievements would still be racing toward them at light speed, yet to arrive. This creates a cosmic irony. If an advanced civilization in Andromeda detected radio signals from Earth, the earliest transmissions would not yet have reached them. Radio broadcasts began roughly a century ago, which means our signals have traveled about 100 light years, a tiny fraction of the distance to Andromeda. From their perspective, Earth is radio silent, a quiet world showing no signs of technological civilization. They would have no way of knowing that creatures on this planet had learned to harness electromagnetic waves. That information is still en route, crawling across the void at light speed, carrying news of our existence to recipients who may not receive it for millions of years. The same logic applies in reverse. If civilizations exist in distant galaxies, they may have built great empires, developed technologies beyond our imagination, risen and fallen countless times, but the light from those events has not yet reached us. We see their galaxies as they were millions or billions of years ago. Any messages they sent would take just as long to arrive. The universe is filled with delayed correspondence, letters crossing in the cosmic mail, news perpetually out of date. This introduces a strange kind of relativity to existence. There is no universal now. The present you experience is not shared by observers in distant locations. Your now is their past, and their now is unknowable to you until their light reaches your position. Time and space blend together in this way. Distance is measured in years because the journey of light links the two. We cannot separate where from when. The stars in the night sky form constellations that have looked much the same for all of recorded human history. Orion, Ursa Major, Cassiopeia, these patterns have guided navigators and inspired myths for millennia. But the stars are all moving. Over tens of thousands of years, the constellations will slowly distort as each star travels along its own trajectory through the galaxy. The Big Dipper will bend. Orion will lose his familiar shape. The sky your distant descendants see will look different from yours. But even that future sky will be a view of the past. The light from those rearranged stars will still take years to arrive, carrying information about where the stars were, not where they are. We live, in effect, surrounded by history. Every direction we look reveals the universe at some point in its past. The only truly present moment we can access is the one immediately around us, the light from our immediate environment arriving in nanoseconds rather than years. Everything beyond that is memory, encoded in photons, arriving continuously from across time and space. The telescope is a time machine because looking far away is, by definition, looking long ago. And the deeper we look, the more we learn about where we came from, about the cosmic story that led to galaxies and stars and planets, and eventually, eyes capable of seeing them. There is something both comforting and unsettling in this realization. Comforting because it means the universe preserves its history, writing it in light, broadcasting it endlessly in all directions for anyone with instruments sensitive enough to read it. We can study the past simply by looking at the sky. We can watch the evolution of galaxies, the lives and deaths of stars, the formation of the elements that make up our bodies, all recorded in photons that have survived for billions of years. But it is also unsettling because it reminds us that we can never know the present state of anything beyond our immediate vicinity. The universe we see is always out of date. The stars we admire may have died. The galaxies we photograph may have collided. The civilizations we imagine on distant worlds may have risen and fallen without our ever knowing. We are cut off from the cosmic present, isolated in a bubble of the past, watching ancient events unfold and calling them the night sky. Perhaps this is why the stars have always inspired both wonder and melancholy. They are beautiful, yes, but they are also reminders of our isolation. Each point of light is a message from long ago, a signal that has been traveling while generations lived and died on Earth. We cannot answer back in any meaningful way. We can only receive, observe, record, and wonder what the senders are doing now, knowing we will never know. Our nearest neighbor, 0.24 light years, that is the distance to Proxima Centauri, the closest star to our Sun, and it might as well be a wall. Not because we cannot see it. We can, though just barely, with a good telescope under dark skies. Not because we do not know anything about it. We know quite a lot. We know it is a red dwarf star, about 1/7 the mass of the Sun, glowing with a dim reddish light. We know it has at least 3 planets, including one roughly Earth-sized world orbiting in what might be the habitable zone. We know it flares violently, unleashing bursts of radiation that would challenge any life trying to survive on those nearby worlds. We know all this, gathered painstakingly across decades of observation, and yet Proxima Centauri remains so far away that reaching it is beyond any technology we possess or can reasonably imagine building. 4 light years sounds manageable. It is smaller than most cosmic distances discussed in astronomy. It is a rounding error compared to galactic scales, but translate it into human terms, and the number reveals its true immensity. 4.24 light years equals roughly 40 trillion kilometers. If you started walking today at a brisk pace of 5 kilometers per hour, never stopping to rest, eat, or sleep, you would arrive at Proxima Centauri in about 900 million years. If you drove a car at highway speed, the journey would take roughly 48 million years. If you flew in a commercial jet, cruising at 900 kilometers per hour, you would arrive in something like 5 million years. The Voyager 1 spacecraft, the farthest human-made object from Earth, travels at about 17 kilometers per second relative to the Sun. At that speed, if it were headed toward Proxima Centauri, which it is not, it would arrive in approximately 73,000 years. 73,000 years ago, Homo sapiens were painting in caves. Agriculture had not been invented. The last ice age had not yet reached its peak. Everything we call civilization, every city and empire and technology exists within a window of time shorter than a single Voyager flight to the nearest star. This is the tyranny of interstellar distance. We live in a universe where the gaps between stars dwarf all human experience. The Moon is 3 days away by spacecraft. Mars is a few months. Even the outer planets, at the farthest reaches of our solar system, can be reached within decades using existing technology. But the nearest star requires time spans that exceed recorded history, that exceed the existence of our species, that exceed the duration of civilization itself. Unless we find ways to travel vastly faster than anything we have built, the stars will remain forever out of reach. Proxima Centauri is part of a triple star system called Alpha Centauri. The two larger stars, Alpha Centauri A and B, orbit each other every 80 years at distances ranging from the Sun-Saturn distance to the Sun-Pluto distance. These stars are similar to our Sun, yellow and orange dwarfs, and they have been studied for centuries. The third member, Proxima, is much smaller and fainter, orbiting the inner pair at an enormous distance of about 13,000 astronomical units, taking over 500,000 years to complete a single orbit. Proxima is so far from its companions that some astronomers once debated whether it was truly gravitationally bound to them at all. From Earth, the Alpha Centauri system appears as the third brightest star in the night sky, a brilliant point visible from the southern hemisphere and parts of the tropics. But Proxima itself is invisible to the naked eye. It was discovered only in 1915 by the Scottish astronomer Robert Innes, who noticed its unusually large, proper motion, its apparent drift across the sky compared to more distant background stars. That rapid motion was a clue to its proximity. Stars that appear to move quickly are usually nearby, just as a bird flying past your window seems faster than an airplane at 30,000 feet. Proxima Centauri became even more famous in 2016 when astronomers announced the discovery of a planet orbiting within its habitable zone. Proxima Centauri b, as it was named, has a mass similar to Earth and orbits its star every 11.2 days. Because Proxima is so dim, planets can orbit much closer than Earth orbits the Sun and still receive comparable amounts of energy. Proxima b sits only 7.5 million kilometers from its star, about 5% of the Earth-Sun distance, yet it may receive roughly the same total energy that Earth does. The discovery sparked immediate excitement about the possibility of life on a world so close to our own, astronomically speaking, but proximity is relative. 4 light years is close enough that we can study Proxima b with future telescopes, potentially analyzing its atmosphere for signs of biological activity. It is close enough that a dedicated mission might someday send a spacecraft there. But it is far enough that any such mission would be the most ambitious engineering project in human history, requiring propulsion technologies we have not yet developed, and trip times measured in decades or centuries, even with optimistic assumptions. One proposal, called Breakthrough Starshot, envisions sending tiny spacecraft, no larger than postage stamps, propelled by giant ground-based lasers to speeds approaching 20% of light speed. At that velocity, the journey to Proxima Centauri would take roughly 20 years. The probes would carry cameras and instruments capable of transmitting data back to Earth. Even at light speed, those transmissions would take 4 years to arrive. The entire mission, from launch to receiving images, would span a quarter century at minimum. 20% of light speed is 60,000 kilometers per second. No human-made object has ever traveled anywhere close to that fast. The fastest spacecraft ever, the Parker Solar Probe, reached about 190 kilometers per second during its closest passes to the Sun, less than 1% of the Breakthrough Starshot target. Accelerating even a gram of mass to 20% of light speed requires enormous energy. The Starshot concept relies on keeping the probes incredibly small and using lasers to provide the push from outside the spacecraft, avoiding the need to carry fuel. Even if Starshot succeeds, it offers only a flyby. The tiny probes cannot slow down. They will streak past Proxima Centauri in a matter of hours, gathering what data they can before continuing into interstellar space forever. A mission capable of entering orbit around Proxima b or landing on its surface would require carrying deceleration fuel, which means launching a much larger spacecraft, which means providing much more energy, which means even greater engineering challenges. The distances involved also create profound communication challenges. A signal from Proxima Centauri takes 4.24 years to reach Earth. A message sent and a reply received constitute a minimum round trip of 8.5 years. Conversations become impossible. Instructions become obsolete. Any probe we send to another star system must be autonomous in ways that exceed even our most advanced current robots. It must make decisions, adapt to unexpected situations, and conduct its mission without any possibility of real-time guidance. These challenges have led some to wonder whether interstellar travel is simply impractical for biological beings. Perhaps the only way to cross such distances is to send machines, robotic ambassadors built to outlast centuries of travel, designed to operate indefinitely without human supervision. Or perhaps some future generation will find ways to extend human lifespans, making journeys of decades or centuries survivable for individual travelers. Or perhaps there are physics discoveries yet to come, new understanding of space-time that might reveal shortcuts or faster-than-light possibilities currently unknown. For now, Proxima Centauri remains a tantalizing neighbor we can see but not visit. Its planets may harbor conditions interesting to astrobiologists, perhaps even life itself, evolving independently just 4 light years away. But those 4 light years constitute a gulf that all of human technology cannot yet bridge. We have sent machines to every planet in our solar system, landed probes on moons and asteroids and comets, even placed human footprints on the moon. But the nearest star remains as inaccessible to us as the moon was to the ancient Greeks. We can see it, we can study it, we can dream of going there, but we cannot go. There is a peculiar loneliness in this. The universe is filled with stars, hundreds of billions in our galaxy alone, many of them orbited by planets. The ingredients for life appear common. The conditions for habitability may exist on worlds beyond counting, and yet each stellar system is isolated from every other by these immense light-speed barriers. Even if the galaxy teems with civilizations, they may be forever separated by the travel times between them. Contact might be possible through radio signals or laser pulses traveling at light speed, but visits might be prohibitively difficult for any species bound by the same physics we are. The Fermi paradox takes on new weight in this context. If intelligent life is common in the galaxy, why have we not detected it? One possible answer is simply distance. Civilizations may flourish on planets orbiting distant stars, building technologies and cultures and histories of their own, yet remain forever unaware of each other, because the gaps between them are too vast to cross. A message sent at light speed takes thousands of years to traverse the galaxy. A reply takes thousands more. Conversations unfold across geological timescales. No single generation would ever complete an exchange. Civilizations might rise and fall in the time between question and answer. This isolation may be the default condition for intelligent life in the universe. We imagine contact with aliens as a meeting, a handshake, a moment of recognition. But reality may be far more melancholy. Contact might mean only the detection of ancient signals from civilizations that no longer exist, archaeological whispers from the dead, or it might mean sending messages that will not be received for millennia, addressed to descendants we will never know. The light year is not just a unit of distance. It is a measure of separation, of silence, of the profound aloneness that comes from living in a universe too large to traverse. Proxima Centauri, our nearest neighbor, is both a beacon and a reminder. It shows us that other stars are real, that other worlds exist, that the universe extends beyond our small solar system into realms we are only beginning to explore. But it also shows us the price of cosmic distance, the walls built by light itself, the isolation that comes from living in a universe where even the closest places require journeys longer than human memory. When time itself bends, there is a way to cheat the cosmic speed limit, not by traveling faster than light, which remains forbidden, but by manipulating time itself. Einstein's theory of special relativity revealed something profound and counterintuitive about the universe. Time does not flow at the same rate for everyone. It slows down for objects in motion. The faster you travel through space, the slower you travel through time. And at speeds approaching that of light, this effect becomes dramatic enough to transform interstellar journeys that would otherwise take centuries into voyages lasting mere years for the travelers themselves. This phenomenon is called time dilation, and it is not theoretical speculation. It has been measured with extraordinary precision using atomic clocks, particle accelerators, and satellites. It is real. It happens. And it offers a strange kind of hope for a universe otherwise defined by the tyranny of distance. To understand time dilation, we must return to a fundamental insight of special relativity. The speed of light is constant for all observers. No matter how fast you travel, no matter in what direction, light always moves past you at the same velocity. This seems impossible by everyday intuition. If you are in a car driving at 60 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the sidewalk sees the ball moving at 80 kilometers per hour. Speeds add. That is how the world appears to work at ordinary velocities, but light does not follow this rule. If you shine a flashlight while traveling at half the speed of light, an observer standing still does not see the light moving at 1.5 times light speed. They see it moving at exactly light speed. The photons ignore your motion entirely. This constancy is woven into the fabric of space-time. It is not a quirk of light, but a fundamental property of reality. For this to be true, something else must bend. That something is time. When objects move relative to each other, their clocks tick at different rates. A clock on a fast-moving spacecraft runs slower than an identical clock on Earth. The difference is negligible at ordinary speeds, fractions of nanoseconds, but it grows rapidly as velocity increases. At 90% of light speed, a moving clock ticks at roughly 44% of its normal rate. At 99% of light speed, it ticks at about 14%. At 99.9%, clocks nearly stop, running at less than 5% of their normal pace. This is not a mechanical effect. It is not that the clock's gears run slower or its electronics malfunction. Time itself, the actual passage of seconds, slows down for the moving object. Everything on that spacecraft experiences less time. The clocks, the equipment, the people, their heartbeats, their thoughts, their aging. A journey that takes decades according to observers on Earth might take only years according to travelers aboard the ship. Consider the famous thought experiment known as the twin paradox. Two identical twins are born on Earth. One stays home living an ordinary life. The other boards a spacecraft and travels to a star 10 light-years away at 90% of the speed of light. From Earth's perspective, the outbound journey takes about 11 years. The return journey takes another 11 years. 22 years pass on Earth during the round trip, but for the traveling twin, time passes more slowly. At 90% of light speed, the time dilation factor is roughly 2.3. The traveling twin experiences only about 9.5 years of subjective time during the journey. When the spacecraft returns to Earth and the twins reunite, the traveler is 9.5 years older than when they left, while the stay-at-home twin has aged 22 years. They are no longer the same age. The traveler is now more than a decade younger than their sibling. This is not a paradox in the logical sense. It does not create a contradiction. The situation is asymmetric. The traveling twin underwent acceleration to leave Earth, deceleration to stop at the distant star, acceleration to begin the return journey, and deceleration to stop back at Earth. These changes in motion break the symmetry between the two twins. the stay-at-home twin remained in an inertial frame, while the traveler changed frames multiple times. Special relativity tells us that the traveler genuinely experiences less elapsed time. Experiments have confirmed this effect repeatedly. In 1970, physicists Joseph Hafele and Richard Keating placed atomic clocks on commercial airliners and flew them around the world, some traveling eastward with Earth's rotation and some westward against it. When the clocks were compared to identical clocks that remained on the ground, they had drifted apart by exactly the amounts predicted by relativity, accounting for both velocity-related time dilation and the gravitational effects on time from altitude differences. The discrepancies were tiny, tens of nanoseconds, but they matched the theoretical predictions precisely. More dramatic confirmations come from particle physics. Muons are unstable subatomic particles created when cosmic rays strike Earth's upper atmosphere. They decay very quickly, with an average lifetime of about 2 microseconds in their rest frame. Given this short lifespan and the altitude at which they are created, classical physics predicts that virtually no muons should survive to reach the surface. They should decay long before they complete the journey. But in fact, many muons do reach ground level. The explanation is time dilation. The muons travel at speeds approaching that of light, and from our perspective, their internal clocks run slowly. Their 2 microsecond lifetime stretches to many microseconds in our reference frame, giving them enough time to reach the surface before decaying. What does this mean for interstellar travel? It means that the subjective duration of a journey can be much shorter than the time that passes for observers at the origin and destination. A ship traveling at 99% of light speed to a star 100 light-years away would, from Earth's perspective, take about 101 years to arrive. But for the passengers aboard, only about 14 years would pass. At 99.9% of light speed, the travelers would experience roughly 4.5 years, while over a century rolled by on Earth. Push even closer to light speed, and the compression becomes extreme. At 99.99% of light speed, a century-long journey by external clocks becomes about 16 months for the travelers. At 99.999%, it shrinks to about 5 months. In principle, you could cross the entire observable universe in a human lifetime if you could accelerate to speeds sufficiently close to light. The journey would appear to take billions of years to outside observers, but for you, only decades might pass. This is not free. Accelerating to such speeds requires enormous energy. The closer you get to light speed, the more energy is needed for each additional increment of velocity. At speeds very close to light, the energy required approaches infinity. No finite power source can push a massive object all the way to light speed, but you can get arbitrarily close, and the closer you get, the more time compresses. There is also the problem of what you return to. A traveler who departs Earth at near light speed and journeys to distant stars will return to an Earth that has aged far more than they have. Everyone they knew before the journey will be dead. Their civilization may have transformed beyond recognition. They become time travelers, not by moving backward in time, but by moving forward at a slower rate than everyone else. emerging into a future they cannot rejoin in any meaningful way. This creates a profound asymmetry between travelers and those who stay behind. An astronaut departing for a star 50 light-years away at 99% of light speed would experience roughly 7 years of travel each way, about 14 years total. But 100 years would pass on Earth. The traveler would return to a planet where great-grandchildren of their contemporaries now lived, where languages had shifted, where technology had advanced through multiple generations, where the very cities they knew might have been replaced by something unrecognizable. They would be a living fossil, a person from a century ago, still young and vital, unable to reconnect with a world that had moved on without them. This is not merely a thought experiment. It is the mathematical consequence of our best confirmed theory of physics. Any civilization that develops near light speed travel must grapple with these implications. Crews sent to distant stars would be volunteers for a one-way trip into the future. They might found colonies that flourish for generations before any report reaches Earth. They might return to find humanity extinct or transformed into something beyond recognition, or spread across thousands of worlds speaking languages that evolved long after the travelers departed. The relativity of time makes interstellar travel possible in principle, but deeply strange in practice. Science fiction has explored this theme extensively, but it is rooted in real physics. The relativistic travelers in stories about generation ships and interstellar voyages face genuine consequences predicted by Einstein's equations. The equations work, they have been tested, and they tell us that the flow of time is not absolute, that motion through space affects motion through time, that the faster you travel, the more the universe ages around you while you remain relatively young. There is even a more extreme form of time dilation caused not by velocity, but by gravity. Einstein's general theory of relativity, which extends special relativity to include gravitational effects, shows that time runs slower in stronger gravitational fields. A clock at sea level ticks slightly slower than a clock on a mountaintop. A clock near a black hole would nearly stop compared to clocks far away. This gravitational time dilation must be accounted for in GPS satellites, which experience both higher altitude and higher velocity than surface clocks. Without corrections for these relativistic effects, GPS positions would drift by kilometers per day. The universe, it seems, does not permit faster than light travel, but it offers a consolation. Time is flexible. The speed limit applies to motion through space, but motion through time can be adjusted by how fast you travel through space. For a photon moving at light speed, time does not pass at all. Emission and absorption are the same instant from the photon's perspective. For travelers approaching that speed, time slows but does not stop, allowing them to cover distances that would otherwise require impossibly long journeys. Whether humanity will ever build spacecraft capable of significant relativistic velocities remains unknown. The engineering challenges are immense. The energy requirements are staggering. A spacecraft accelerating continuously at 1 g, the comfortable pull of Earth's gravity, would approach the speed of light within about a year. But providing 1 g of acceleration for a year requires vast amounts of energy. Current rocket technology cannot come close. Proposed solutions include nuclear pulse propulsion, antimatter engines, laser-driven sails, and concepts even more exotic. None have been built. None have been tested at the scales required for interstellar travel. Yet the physics is settled. Time dilation is real. And it means that the light years separating us from other stars, while impossibly long by Earth time, might someday be crossable within a human lifetime by travelers willing to accept that everyone they left behind will be gone when they return. The price of the stars is not just distance, it is disconnection from everything and everyone you knew. The relativistic traveler is a refugee from their own time, arriving in a future where they are a stranger. Voyager's lonely milestone. Somewhere out there, beyond the orbit of Neptune, beyond the Kuiper Belt, beyond the boundaries of what most people think of as our solar system, a small spacecraft continues its silent journey into the void. It carries a golden record etched with sounds and images of Earth, a message in a bottle cast into the cosmic ocean. Its transmitter still functions, sending a feeble whisper back toward home, a signal so weak that the entire Voyager power output is less than the energy required to light a refrigerator bulb. And soon, in late 2026, this tiny emissary will reach a milestone that puts into stark perspective everything we have discussed about light years and cosmic distances. Voyager 1 will be one light day from Earth. One light day. The distance light travels 24 hours, roughly 26 billion kilometers. It sounds almost modest compared to the light years separating us from other stars. And yet reaching this distance has taken Voyager 1 nearly 50 years of continuous travel. 50 years of drifting through the darkness at 17 kilometers per second, faster than any bullet, faster than any vehicle most humans have ever conceived, and still it has only reached one light day. Voyager 1 launched on September 5th, 1977, 16 days after its twin, Voyager 2. Both spacecraft were designed to take advantage of a rare planetary alignment that occurs roughly once every 175 years, allowing a single spacecraft to visit multiple outer planets by using each one's gravity to sling it toward the next. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, gathering data that revolutionized our understanding of these giant worlds and their moons. It discovered active volcanoes on Io, hinted at a subsurface ocean on Europa, revealed the complex structure of Saturn's rings, and photographed Titan's thick orange atmosphere. After Saturn, Voyager 1's trajectory carried it upward out of the plane of the planets, beginning its long climb into interstellar space. Its sister ship, Voyager 2, went on to visit Uranus and Neptune, becoming the only spacecraft ever to explore those distant ice giants. But Voyager 1 took the faster path, trading additional planetary encounters for higher velocity. It has been the most distant human-made object from Earth since 1998. In 2012, Voyager 1 officially entered interstellar space, crossing the heliopause, the boundary where the solar wind gives way to the interstellar medium. This transition was confirmed by measuring the density of charged particles around the spacecraft. Inside the heliosphere, the bubble of solar influence that surrounds our Sun, charged particles are predominantly from the Sun itself. Outside, they come from other stars, from supernovae, from the general cosmic background. Voyager 1 detected this change, sending back data showing it had left the Sun's domain and entered the space between the stars. But leaving the solar system is not the same as leaving the Sun's gravitational influence. The Oort cloud, a hypothetical shell of icy bodies surrounding our solar system, may extend as far as 100,000 astronomical units from the Sun, or roughly 1.5 light years. By that definition, Voyager 1 is still deep within our solar system, barely 0.1% of the way to the Oort cloud's outer edge. It will take another 300 years for Voyager to exit the inner Oort cloud, and perhaps 30,000 years to clear the outer boundary entirely. Reaching the nearest star, Proxima Centauri, would take over 70,000 years, and Voyager's not even heading in that direction. These numbers expose the true scale of interstellar distances. Our fastest spacecraft, after nearly 5 decades of travel, has covered less than a day's worth of light. To cover a year's worth at Voyager's current speed would take nearly 20,000 years. To cover the 4.24 light-years to Proxima Centauri would take, as mentioned, over 70 millennia. The stars are not just far away. They are incomprehensibly, absurdly, impossibly far away by any measure of human technology or experience. And yet Voyager persists. Its radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity, continue to function, though their output drops by about 4 watts per year. In 1977, the generators produced about 470 watts. Today, they produce around 220. Every few years, mission controllers must shut down another instrument or heater to conserve power, squeezing every possible watt from the dwindling supply. By the early 2030s, there may not be enough power to operate any scientific instruments at all. By 2036, there may not be enough to keep the spacecraft communicating with Earth. When that day comes, Voyager 1 will continue traveling, silent and dark, a dead machine coasting through interstellar space for millions of years. It will pass within 1.6 light years of a star called Gliese 710 in roughly 1.3 million years, though it will not enter that star's planetary system. It will drift through the galaxy essentially forever, unless something collides with it, a vanishingly unlikely event in the emptiness between stars. The golden record it carries was designed to survive this eternity. Encoded on its surface are 116 images showing life on Earth, greetings in 55 languages, sounds of nature from wind to whales, and 90 minutes of music ranging from Bach to Chuck Berry. The record is shielded by an aluminum cover electroplated with uranium-238, which decays slowly enough that its half-life can be used to date when the record was created, should any finder wish to know. Instructions for playing the record, written in symbolic language based on the hydrogen atom, are etched onto the cover. The chances of any extraterrestrial civilization finding Voyager are essentially zero. The spacecraft is tiny, unlighted, and traveling through a volume of space so vast that the odds of accidental encounter approach impossibility. The golden record is less a practical communication and more a statement of hope, a message saying that we were here, that we reached beyond our world, that we dared to imagine someone might someday listen? The one light day milestone is significant not because it represents a boundary of any physical importance, but because it offers a concrete way to understand Voyager's journey in terms of light travel time. At one light day, a signal from Voyager takes 24 hours to reach Earth. Mission controllers send a command in the morning and receive acknowledgement the following morning. Conversations are impossible. Even simple exchanges require days. The spacecraft operates almost entirely on its own, following programs uploaded years ago, reporting its status to a planet that receives the news a full day late. This delay will only grow. Every year, Voyager travels about 3.5 astronomical units farther from the Sun, adding roughly another half hour of light travel time. By the time its power fails, transmissions may take more than 30 hours each way. The spacecraft will slide beyond routine contact, its final signals fading into the noise, its position known only through extrapolation of its trajectory. There is something deeply moving about Voyager's situation. It was built by human hands in the 1970s, launched with technology that seems almost primitive by today's standards, and it continues to function nearly half a century later, farther from home than anything we have ever sent. It carries our message, our music, our hope into a darkness that we cannot ourselves penetrate. It goes where we cannot follow, at least not yet. Voyager's longevity is itself remarkable. The spacecraft was designed for a 4-year mission to Jupiter and Saturn. It has now operated for nearly 50 years, continuing to return scientific data from a region of space no instrument had ever sampled. Its systems have degraded, its power has dwindled, but it persists. The engineers who built it are retired or gone. The computers that designed its trajectory had less processing power than a modern smartphone. Yet Voyager endures, a monument to an earlier era of exploration, still contributing to our understanding of the cosmos. The scientific return from Voyager's interstellar mission has exceeded all expectations. The spacecraft has measured the density and temperature of the interstellar medium, the magnetic field between the stars, the flux of cosmic rays from distant supernovae. It has detected the boundary where the Sun's influence ends and the galaxy's influence begins. It has shown us that this boundary is dynamic, pushed and pulled by changes in solar activity, a living membrane separating our star's domain from the vast ocean beyond. None of this could have been learned from Earth. Only by sending a machine to the edge could we discover what the edge is like. The one light day milestone is also a reminder of what light days and light years actually mean in human terms. One light day is the result of 50 years of travel at 17 kilometers per second. One light year is 365 times farther. 4 light years, the distance to the nearest star, is over 1,400 times farther. The scales are staggering. Our fastest achievements barely register on the cosmic odometer. If we want to reach the stars in human lifetimes, we need technologies far beyond what we currently possess. We need spacecraft that can travel not at kilometers per second, but at significant fractions of the speed of light. We need propulsion systems that can accelerate continuously for years. We need energy sources that can sustain such acceleration, we need solutions to problems we have not yet fully understood. Voyager shows us both our capability and our limitation. We can build machines that function for decades in the harshest environment imaginable. We can send our instruments beyond the boundaries of the sun's influence. We can touch interstellar space, but we cannot yet cross it. The stars remain light years away, and we have traveled only light hours. One day, perhaps, a future spacecraft will pass Voyager, traveling faster, going farther, closing the gap between here and the stars. Voyager will still be out there, drifting, carrying its golden record, a relic of an earlier age of exploration. It will be overtaken and left behind, the first of many ambassadors to the cosmos. Until then, it remains our farthest reach, our longest throw, our most distant handshake with the universe, crossing its one light day milestone as a testament to what human curiosity and engineering can achieve, and a reminder of how far we still have to go. The edge of everything we can see. The universe is 13.8 billion years old. Light travels 1 light year per year. Logic suggests that the farthest we could possibly see is 13.8 billion light years in any direction, the distance light has traveled since the Big Bang. But the observable universe is actually much larger than this. Its radius extends approximately 46.5 billion light years. Its diameter spans 93 billion light years. How can we see farther than light could have traveled in the age of the universe? The answer involves one of the strangest features of cosmology. Space itself is expanding, and it has been expanding since the very beginning. When astronomers speak of the observable universe, they mean everything from which light has had time to reach us since the cosmos began. This is a sphere centered on Earth, not because Earth is special, but because we can only observe from our own location. Every other point in the universe has its own observable sphere, centered on that point. The edges of these spheres are called cosmic horizons, and beyond them lies territory we cannot access, regions from which no signal has yet arrived, and, in some cases, regions from which no signal ever will. The expansion of space complicates what seems like simple geometry. In the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. Space stretched faster than light could travel through it. Regions that were once close together were flung apart at velocities exceeding light speed. This does not violate relativity because nothing was moving through space faster than light. Space itself was expanding, carrying everything along with it. The distinction is subtle but crucial. Objects embedded in space cannot exceed light speed relative to each other locally, but space itself can stretch at any rate, and distant regions can recede from each other faster than light due to the expansion between them. Because space has been expanding since the Big Bang, objects that emitted light 13.8 billion years ago are now much farther away than 13.8 billion light years. The light left when those objects were closer, traveled through expanding space for billions of years, and arrived at Earth having covered a constantly stretching path. When we measure the current distance to those objects, accounting for all the expansion that occurred during the light's journey, we find they are now about 46 billion light years away. We see them as they were in the distant past, but they have since moved far beyond the point where they appear to be. This leads to a peculiar situation. The cosmic microwave background, the oldest light we can detect, was emitted roughly 380,000 years after the Big Bang. At that moment, the matter that produced this radiation was about 42 million light years from the matter that would eventually become Earth. But the light has been traveling through expanding space for 13.8 billion years. Today, that same matter is approximately 46 billion light-years away. We see its ancient image frozen in time from when the universe was young, but the objects themselves have long since evolved into galaxies that are now receding from us faster than light. This creates a cosmic horizon in the truest sense. Objects currently beyond a certain distance are receding so fast due to the expansion of the space between us that their light will never reach Earth. They have crossed the cosmic event horizon. We can never observe what they are doing now, and we will never receive any signal they emit from this point forward. They are causally disconnected from us, effectively existing in a separate universe as far as information exchange is concerned. The observable universe contains approximately 2 trillion galaxies, each with hundreds of billions of stars. The total number of stars is estimated at around 200 sextillion, a 2 followed by 23 zeros. This is more stars than there are grains of sand on all the beaches of Earth. And this is only what we can see. The full universe, almost certainly, extends far beyond the observable portion, perhaps infinitely. Our cosmic horizon is not a wall or an edge. It is simply the limit of our vision, the boundary beyond which light has not yet had time to arrive or never will. Within the observable universe, we can trace cosmic history. The James Webb Space Telescope has detected galaxies that formed less than 300 million years after the Big Bang. These are seen as they were over 13.5 billion years ago, when the universe was a toddler by cosmic standards. The galaxies appear small, irregular, and intensely active, churning out stars at furious rates. They represent the first structures to emerge from the primordial fog, the ancestors of everything that exists today. Look at closer distances, and you see more recent history. Galaxies a few billion light-years away show the universe in its adolescence, already organized into spiral and elliptical forms. Galaxies only hundreds of millions of light-years away appear relatively similar to our own Milky Way, products of billions of years of cosmic evolution. And galaxies in our local group, within a few million light-years, show the universe essentially as it is today, the light travel time being negligible on cosmic timescales. The cosmic microwave background represents the farthest back we can see using light. Before this radiation was released, the universe was a dense plasma of charged particles that scattered photons continuously. Light could not travel freely. The universe was opaque, like trying to see through fog. When the plasma cooled enough for electrons to combine with protons and form neutral atoms, the fog cleared. Light suddenly could travel without interference, and it has been traveling ever since, carrying an image of that moment across the expanding cosmos. This background radiation is remarkably uniform, showing the same temperature in every direction to within 1 part in 100,000. The tiny variations that do exist correspond to slight density differences in the early universe, regions that were fractionally denser or less dense than average. These variations became the seeds of cosmic structure. Denser regions attracted more matter through gravity, eventually forming galaxies and galaxy clusters. Less dense regions became the voids that separate cosmic structures today. The entire large-scale organization of the universe was imprinted in those tiny temperature fluctuations visible in the microwave background. Beyond the cosmic microwave background, we cannot see with light, but we may eventually detect signals from even earlier epochs using gravitational waves or neutrinos, which interact so weakly with matter that they could escape from the opaque early universe. The cosmic neutrino background, if we could detect it, would show us the universe as it was only 1 second after the Big Bang. Primordial gravitational waves might carry information from the inflationary epoch itself, a trillionth of a trillionth of a trillionth of a second after the beginning. These are frontiers yet to be explored. The observable universe is expanding in 2 senses. Space itself continues to stretch, carrying galaxies apart from each other and slowly pushing some beyond our cosmic event horizon. But our observable sphere is also growing because light from more distant regions continues to arrive for the first time. Every second, light from slightly farther away reaches Earth, expanding our view of cosmic history. We see farther into the past with each passing moment, though the rate is negligible on human time scales. Astronomers estimate that the entire universe beyond the observable portion may be vastly larger than what we can see. Some models suggest it could be infinite. Others propose it might be finite but unbounded, curving back on itself like the surface of a sphere, so that traveling in a straight line, long enough, would return you to your starting point. Current measurements of cosmic geometry are consistent with a flat, infinite universe, but they cannot rule out slight curvature that would indicate a finite cosmos. We may never know for certain. The 93 billion light-year diameter of the observable universe is itself humbling enough. Within it lie more galaxies than humans could count in 1 million lifetimes, more stars than words ever spoken, more planets than we can imagine, and yet it may be the merest sliver of a far grander whole, a window onto a cosmos that extends without limit in every direction, filled with structures and perhaps intelligences that we will never detect because the light from them will never reach us. This is the scale against which a light year must be measured. 1 light year, 9.46 trillion kilometers, seems incomprehensibly large until you consider that the observable universe spans 93 billion of them. Our galaxy, the Milky Way, is 100,000 light-years across, a dot in a sphere billions of times wider. The distance to Proxima Centauri, 4.24 light-years, is so small on this scale that it rounds to 0. We inhabit a universe of staggering size, and light-years are the only units large enough to make discussion possible. The cosmic horizon reminds us that there are limits to knowledge. We cannot see beyond the edge of the observable universe. We cannot know what lies there. We cannot receive any information from regions that have crossed the event horizon. The universe keeps secrets, holding back portions of itself that we will never access, no matter how advanced our technology becomes. Light itself the fastest messenger, cannot bring us news from everywhere. Some distances are simply too great. This creates a strange form of cosmic censorship. The universe may be infinite, filled with galaxies and stars and perhaps civilizations beyond counting, yet we will never know about most of it. Our observable bubble is finite, bounded by the cosmic light horizon, and everything beyond is as inaccessible to us as the interior of a black hole. We can speculate, we can theorize, we can build mathematical models of what might exist beyond our view. But we cannot observe, cannot measure, cannot confirm. Some physicists find this troubling. Science depends on observation and experiment. A universe filled with unobservable regions seems to violate the principle that meaningful statements must be testable. Others embrace the humility that cosmic horizons impose. Perhaps the universe is not obligated to reveal all its contents to any particular observer. Perhaps the existence of horizons is a feature rather than a bug, a built-in reminder that we are small beings in a vast cosmos, privileged to see what we can see, but not entitled to see everything. The expansion of the universe adds a poignant dimension to this picture. Not only are distant regions beyond our current view, but some regions are receding so fast that their light will never reach us no matter how long we wait. They have crossed the cosmic event horizon and are lost to us forever. Every moment, photons from distant galaxies that were once within our potential future view are being redshifted into oblivion as those galaxies accelerate beyond the speed of light relative to us. The observable universe, vast as it is, will eventually shrink from our perspective as cosmic expansion carries more and more galaxies beyond the horizon. In the far future, trillions of years from now, the expansion of the universe will have carried all other galaxies beyond the observable universe of any observer in the Milky Way. Future astronomers, if any exist, will see only their own galaxy floating alone in an apparently empty cosmos. The cosmic microwave background will have redshifted to undetectable wavelengths. All evidence of the Big Bang, of other galaxies, of the vast cosmic web of structure will be gone. They will have no way of knowing that the universe was once filled with hundreds of billions of other galaxies. The cosmic horizon will have closed in, erasing history, leaving only isolation.